So what I want to do is talk first a bit about multinomial and conditional logit models. Essentially, so this is literature that goes back to the early 70s when McFadden was working on these models when he was helping the design of the mass transit in the Bay Area. And so he developed a whole slew of multinomial choice models. So first I'll talk about some of the basic ones. Then I'll talk in some detail about the problems with some of the simple models, in particular with the independence of irrelevant alternatives. Then I'll talk about three generalizations of the conditional logit models that don't have the independence of irrelevant alternative properties. And then I'll talk a little bit about a set of methods that has become very popular in industrial organization associated with the work by Barry Levinson and Pecos. And I'll talk a little bit about models with multiple unobserved choice characteristics and hedonic models. And so a lot of the empirical literature in the last decade or so here has been in industrial organization, which is not generally my area of expertise. So I hope you bear with me here. But nevertheless, I'll try to give some comments and try to put some of these things in perspective. So I'll start with some of the multinomial choice models that McFadden developed in the early 70s. And I'll talk at length sort of about the issues with those models, the independent of the irrelevant alternatives property, and why that's particularly unappealing in some of the settings that have been considered in industrial organization, where people have looked at these models in settings with relatively large number of choices. I mean, some of McFadden's work just looked at cases where there were very few choices. So he was looking at the design of BART, and so he was interested in whether people would commute to work by car, or by mass transit, or in various forms. So there were relatively few. There were more than two choices, but there were relatively few choices. I mean, there's another paper using some of these models looking at the demand for dryers, where the choices were not buying a dryer, buying an electric dryer, buying a gas dryer. But they were almost all the applications he was focused on had very few choices. In contrast, in these industrial organizations where people look at the demand for differentiated products, there's this large number of choices. Two of the most prominent examples involve people buying cars. So there's a huge number of choices there. You can kind of narrow it down a little bit, but in the end, there's going to be on the order of 50 or 100 different choices. And the problems with some of the properties of these early models become much starker in those settings. And so I want to look at three alternatives to multinomial logit models, to conditional logit models that don't have this IIA property. Nested logit models, sort of relatively unrestricted multinomial probit type models, and random effects models. And so I'll argue that the random effects approach is a very attractive way of dealing with violations, with concern about violations, about independence of irrelevant alternatives that either nested logit or these unrestricted multinomial probit models. And then in the second part of the lecture, I'll talk about this work by Barry Levinson and Pecos, where they use these random effects models, but they generalize this in a number of ways. In particular, they allowed they developed a very specific model that you could actually estimate using only aggregate choice data. So in the case of demand for differentiated products, there would be market shares for these products in different markets. In addition, they allowed for endogenous choice characteristics as well as unobserved choice characteristics. And so we'll look at some detail at their model and sort of how you would go about estimating that, as well as sort of what I find the less attractive features of those models, and in which way you may want to do things differently from the way they did it in their original 96 paper. So the whole lecture is about multinomial choice, but there's more than two choices. So the outcome is some denoted here by y takes on yi takes on non-negative unordered integer values between 0 and j. So there's j plus 1 choices. And so the classical examples are the commuting choices that McFadden looked at: bus, train, or car. In labor, it could be employment status. People could be employed, unemployed, or out of the labor force. And sort of the classical I/O example is car choices, where you can buy a whole different set of models as well as different brands and as well and various versions of these things. And so, in order to explain the distribution of these choices, we're going to have two different types of covariates available. One set will be individual-specific variables, things associated with the decision maker, with the individual making the choice, denoted here by CI. And so those are things like age, income, education. Those are fixed characteristics of the individual. And the important part of being fixed is that they don't vary by choice. In addition, we're going to have some variables that vary by choice. And so these are characteristics of the choice. They may also vary by individual. That's going to be allowed for. That's not going to be essential. The key thing is that they vary by choice. And so one of the most important ones in this literature on demand for differentiated products would be the price of these choices, which typically doesn't actually vary by the individual. But in some of the original McFadden examples, if you think about commuting choice, a characteristic of a choice would be how the price for a particular individual to commute to work by car or by train, and certainly there both the cost in terms the monetary cost could vary by individual as well as by choice. But in addition, other aspects of a choice could vary by the individual as well as by the choice, namely the commuting time. And so even in the demand for differentiated products, it could be that there is some price variation by individual, or certainly by groups of individuals. So in general, we're going to have these covariates xij, for which it's essential that they vary by choice. So in general, the choice, we'll refer to them as choice characteristics, but they may also vary by individual. And so the starting point, sort of, and this is in some sense a very direct generalization of just a simple binary logit. Suppose we only have individual-specific covariates. A natural way of modeling the choice would be to generalize the binary logit to this multinomial logit, where you make the probability of choice j a function of these individual covariates in this particular form. It's for the probability for choice j is e to the power c prime gamma j over this divided by the sum of the e to the power c prime gamma l, where you sum over all the other choices. And so here the gamma j's are choice-specific parameters, and the z's are individual-specific choice-invariant covariates. And so this works perfectly well. If you generalize this by allowing the functions of z in there, then no matter what the actual joint distribution of the data is, no matter what these probabilities actually look like, you can always approximate them arbitrarily well by some function of this form, where you may need, in addition to the z's entering linearly, you may need higher order terms. But in principle, there's nothing very restrictive about this setup. If all you have is a set of covariates that varies at the individual level, then you could approximate things arbitrarily well using this model. And so in some sense, this generalizes very easily to the case where you have choice-specific covariates. You could just define the Z to be the stacked version of all these choice characteristics. And so you can always model the choice probabilities as some general function of all the choice and individual characteristics, and that would in the end fit very well. It wouldn't be a very attractive way to go. It wouldn't be very easy to interpret the parameters. But the point is that this functional form isn't really all that restrictive, but it doesn't tie in very nicely to economic theory if you do this with the Z's consisting of these stacked versions of the choice-specific covariates. And so the second version of these models that McFadden developed is the conditional Logit model. In a simple case, suppose that we only have choice-specific covariates, so we have now capital J plus 1 factors of covariates. And so think of these as just prices for the different choices, as well as, say, quality of these different choices. Then the implication of the conditional Logit model is that the probability of the choice being of choice J is e to the power xij prime beta divided by the sum over all choices of that expression. And now the xij's are choice specific, but the beta is common to all choices, and sort of like the multinomial Logit model. This model is very easy to estimate. It has a very well-behaved likelihood function, strictly concave. It works. It's extremely easy to implement. Now, the first comment I want to make relating these two models, essentially sort of dismissing the multinomial Logit model from further discussion, is that we can just view the multinomial Logit model as a special case of this. We could just define the choice-specific characteristics in the following way, where for the first choice, we put in the individual characteristics in the first part of the vector of characteristics and put in zeros everywhere else. Do that for all the other choices. And now, even if we start off with a multinomial Logit model, we can in the end write it as a conditional Logit model. So for any of the statistical issues, we can just only focus on the conditional Logit model and always think of the choice characteristic potentially consisting of individual characteristics interacted with the dummy for each of the choices. Now, the second comment, so that's sort of more interesting. So that sort of gives much more motivation for thinking about the conditional Logit model. This relates to the way McFadden developed these models originally. So he was very interested in making sure that the choice model was consistent with individuals maximizing utility. And so what the point where he started from was to think of the utility associated with a particular individual, associated with a particular choice. And so he modeled that as linear in these choice characteristics xij, with at this point a common coefficient beta, plus some idiosyncratic error term. and then given all these utilities for these j+1 choices, the individual I chooses option J, or makes choice J, if that choice gives the highest level of utility, if that exceeds the utility for all the other choices. Now, sort of a natural thing from certainly from the Econometrics at that in the 70s might have been to use a normal distribution for these epsilon ij's. That would make the choice probabilities very complicated functions of the parameters, even if these epsilon ij's were independent, because now you would be looking at the maximum of these utilities, which essentially is going to involve order statistics of these normal distributions. That doesn't work very well. And instead, it works much better if we use an extreme value distribution, which is sort of a slightly funny distribution. It's not symmetric around 0. It does have a mode at 0, but the mean is positive, and so it's slightly skewed to the right. But if you use that distribution, you get things simplify enormously, and you get the implication is that the choice Y follows the conditional Logit model, which ends up being extremely easy to estimate relative to this type of model with normal errors. So this is all very well, and so up to here, these models are extremely easy to estimate. Which obviously was very important at the time that McFadden was working with these models. But there's also some concerns with these models, and also pointed out at the time by McFadden. And so the key issue with this model is this independence of irrelevant alternatives. And so we'll spend a little bit of time on that. So if you look at the conditional probability, so given that we have j+1 choices, if you look at the conditional probability that someone makes choice J, given that I tell you they're making choice either choice J or L, you can just figure that out from the joint probability of all these choices, and that turns out to be a very simple function, very similar to the unconditional probability, but depending only on and that's the IIA property, it depends only on the characteristics of the choices you're conditioning on, J and L in this case, and not on any other choices of, not on the characteristics of any other alternatives M. So at some level, that's sort of seems fine. If it's sort of partly coming from so one simple way of changing that property would just be to part of that property comes from the fact that the utility for choice J only depends on the characteristics of choice J. But that seems very reasonable. There doesn't seem to be any reason why the utility for choice J should depend on characteristics of any other goods. So at some level, this may seem like a very reasonable property. Trouble, though, is that if we take this model more seriously, if we interpret this really as a structural, causal, behavioral model that tells us what choices people would make if we change the characteristics of the products, you get into very awkward. You get very awkward implications of this property. So let me sort of elaborate on that a little bit. And so what I want to show is that these models, that the conditional Logit model, even though it may fit very well, as I said before, the same way the multinomial Logit model can be made to fit arbitrarily well, it isn't necessarily very attractive as a structural model because it generates very unrealistic implications. So the example here is one from my Berkeley days, so partly as a tribute to McFadden. So here the choice set is 3 restaurants, Chez Panisse, La Limes, which is where a favorite of McFadden's, and where if you go at the right time of the year, at least it used to be that you would get figs from McFadden's farm. And then there's the third place where the other econometricians would go, which wasn't quite as bad as the name suggested, but it wasn't where McFadden would go. So we have these 3 choices: Chez Panisse, which I guess is well known enough, La Limes, which is also a very good restaurant, and the Bongo Burger. So Chez Panisse and La Limes are very expensive. Bongo Burger was very cheap, but it also was reflected in the quality of these 3 places. And so here I put in some numbers I put in some parameters for the utility function that would generate market shares for Chez Panisse of 10%, for La Limes of 25%, and the Bongo Burger of 65%. And so at this point, the data would be perfectly consistent with this model. And just from these data, there's nothing you could see that is independent of irrelevant alternatives would not be satisfied. The problem is, if you think about the thought experiment, or think about the predictions of what would happen if you changed the characteristics of one of the restaurants. And so the natural thing to think about is what would happen if the price at one of these restaurants changed. And so let's take this. Look at an extreme version of this. Maybe just take one of these restaurants out of business, raising the price to infinity. What the conditional Logit model predicts is that the market share for La Limes would get divided by the 2 remaining restaurants proportional to their original market share. And that the implication is, given that the market share for the Bongo Burger was much larger than that for Chez Panisse, most of the people who would have gone to La Limes when they was still in business, if it goes out of business, would now go to the Bongo Burger rather than Chez Panisse. That just seems very implausible. And so what you would expect, I think the natural thing to expect would be that the people who went to La Limes, if that option was no longer available, would go to a place that is similar. In the end, it would seem that these people would be much more likely to go to a similar restaurant than go to a restaurant that is very different, even though that latter restaurant had a much bigger market share to begin with. And so the implication is that if we want to use these models, if we want to take these models seriously, if we want to use them for predicting the effects of policy changes, of changing the characteristics, and that is obviously in the end what makes these models most interesting. Just describing the patterns in the data isn't all that relevant. Going back to what McFadden was interested in the 70s, he was trying to predict how many people would actually go by train under various scenarios. We need to be able to take these models much more seriously, and at that point, this IIA property is an extremely unattractive one. And so we need to think about what drives that property. We need to think about how we can generalize that. And so one way to think about that is to go back to the latent utility setup, where we specify the utility of choice j for individual I as xij prime beta plus epsilon ij. And in order to make this tractable, the conditional Logit model assumed independence of these extreme value error terms epsilon ij. Now, it's really the independence that drives this IIA property. That's not completely right. You don't get exactly independence of irrelevant alternatives if you used normal errors, but the deviations of that property you would get are not really large enough to make these models more attractive than the conditional Logit model. And so it's really somehow this independence of these error terms. And think about it substantively. Why do we think individuals who would have gone, who had a preference for Lalimes, would have gone to Chez Panisse if Lalimes was out of business? We think that the utility for those individuals at Chez Panisse would be much higher than what it would have been at the Bongo Burger. Partly we would have thought that the epsilon ij for Chez Panisse would have been very similar to the epsilon ij for Lalimes. So somehow we need to allow for some correlation between these epsilon ij's. And so the next couple of minutes, I want to talk about the three ways that of relaxing that assumption. And so, the three things I want to talk about is the nested Logit model, where the researcher a priori groups together sets of choices that are viewed as similar. Implicitly, that's going to allow for non-zero correlation between the unobserved components of those choices within these sets, within these nests, and at the same time, it maintains zero correlation between the unobserved components across nests. So, in terms of that restaurant example, the idea would be to group a priori Lalimes and Chez Panisse together as sort of similar choices, and think of individuals as making a choice first between the two sets, either going to a cheap restaurant or going to an expensive restaurant, and conditional on that choice, choosing between the two expensive restaurants if the choice is to go to an expensive restaurant. And so I'll give a little more detail of that in a minute. A second approach is to just free up that covariance matrix for these epsilon ij's directly. That's slightly more awkward to do in the extreme value case. And so when people started looking at those models, instead of using extreme value errors, they use normal errors. In the end, so this is sort of more of an aside. In the end, the choice between extreme value errors and normal errors there is and should be completely driven by convenience. There's not really anything particular to choose between those substantively. I remember a long time ago seeing it. Actually, let me make two comments there. I think there's a paper by David Cox in the statistical history at some point doing some showing that even in the binary case, you would need thousands of observations before you could tell whether data came from a probit model or a Logit model, because these things are just far too close. Same time, when I teach this stuff, sort of often I've asked students, how should we choose between, sort of just in the binary case, how should we choose between Logit or probit models? And the remarkable thing is that in most cases, the dominant answer is that we should look to economic theory to motivate that choice. And I'm all for. I mean, I think here this discrete choice literature is a very nice example of how economic theory can be extremely useful. But the idea that theory would tell us that the unobserved components would be extreme value rather than normal seems seems surprising. But so here, I think that that is just a completely irrelevant concern, and the fact that the normal errors make it much easier to think about the correlation structure seems a very sensible reason for looking at multinomial probit, sort of unrestricted multinomial probit models, rather than try a very convoluted way of having an unrestricted covariance matrix for extreme value errors. That's separate from the nested Logit model, which is obviously a very elegant way of allowing for that structure, but it's a very different one where you impose a lot of structure on that correlation. The unrestricted one would be very hard to do with Logit errors. So I'll talk about the unrestricted multinomial probit model for a while. And the third way of doing that is the mixed or random coefficient Logit model. And there the idea is that going back to the utility representation, having the utility for choice j for individual I depend on the covariance for that choice interacted, sort of multiplied by a set of coefficients that varies at the individual level. And so here, using this utility maximizing framework is very useful. These betas would vary at the individual level, but it would have very clear interpretations as just the marginal utilities. And there's no particular reason why they should be the same for individuals. And in the end, and this is sort of partly the reason I find it a very attractive way of generalizing the conditional Logit model. It sort of seems to fit in very naturally with the reason why you would think that these individuals who went to Lalims would have gone to Chez Panisse if that had not been available. By revealing their preference for Lalims, they reveal that they're relatively insensitive to price and have strong preferences for quality compared to individuals who went to the Bongo Burger. So now let me move on to give a little more detail about the nested Logit model. So here the idea is to take the full set of choices, partition that set into capital S subsets, so that each choice is in one of these subsets. Within a choice, within a set, within a nest, in this nested Logit terminology, the choice follows a conditional Logit model with a scaled set of parameters. So instead of just with beta, it's with beta divided by an additional parameter, rho sub s, where this rho sub s is going to essentially give us the correlation within the nest. You can have that be common within each nest, or you can have that be nest-specific. Here in this notation, it's a nest-specific correlation. And then the probability of a particular nest turns out to have a remarkably simple form still that also essentially has a conditional Logit form. And so if you just fix all the rows at 1, we're back in the conditional Logit model. But if we allow, and so it's slightly awkward that the row equal to 1 corresponds to 0 correlation between the unobserved components, and row is 0 corresponds approximately to perfect correlation. But that's sort of the terminology. That's the notation that was used originally in that literature. And so another way of thinking about this is that what this setup does is still allow for these marginal extreme value errors, epsilon ij, but instead of having them independent, it has some structure on it. It has some non-zero allows for non-zero correlations with a particular structure on it that keeps the epsilon ij's independent if they're in different nests, but it gives them a common correlation, common non-negative correlation, if they're within the same nest. And so to capture to go back to the example, the way you would capture that example is to have two nests, one of the expensive restaurants and one of the cheap restaurants. And individuals would first choose between the expensive or cheap, and then choose one of the expensive restaurants. Now it turns out the conditional logit was extremely easy to estimate. The likelihood function was strictly concave. It was all very straightforward. Here the likelihood function is a mess. I think it has multiple modes. I don't actually think I've seen any paper that people may have directly maximized the likelihood function. Certainly when McFadden was doing this really wasn't feasible. But it turns out you can exploit this repeated conditional logit structure. And so you can first estimate the scaled coefficients within each nest by only using the choices within that nest, and estimate beta over rho using a conditional logit model. Then you can estimate the rows using the probability of a particular choice by calculating what is known as these inclusive values. So this looks considerably more complicated than it is. In the end, it's just twice using conditional logit, and that gives you consistent root and consistent asymptotically normal random estimators. So there's also results on the covariance matrix here, but this is a perfectly regular estimator. You could, in principle, just bootstrap this, and that would work fine, because this would be very fast. Now, one essentially this example was just for two nests. You can actually do this much more generally, and here is a figure from a paper by Penny Goldberg, which is probably the most impressive example of this setup that I've seen. But she models the individuals choosing cars. And so there's, as I mentioned before, in the end, there's a very large number of choices here. You couldn't, there's a very large number of choices here. A simple conditional logit model would be extremely unattractive. You clearly wouldn't think that individuals would choose a particular foreign luxury car, would go to a completely different type of car if that car got taken off the market. And so the way Penny Goldberg tries to get around the independence of a relevant alternative property is to have this whole sequence of nests where individuals first choose between not buying a car, buying a car, used or old, used or new car. Then she has a number of classes of cars. Then individuals choose between foreign or domestic cars. Then they choose a particular model of car. And so it's a really remarkably detailed nesting structure. But the same principles pretty much apply. You can estimate these parameters. So what this in the end allows for is having correlations at the lowest level for all the models, for all the cars, for all the choices within a particular model. It has additional correlation for choices within these higher level nests, and so in the end, this implies a very flexible structure on the covariance matrix of these epsilon ij's. But still with an enormous amount of structure. There's a number of correlations that are restricted to be zero, and lots of other correlations that are restricted to be the same. But given that in principle, say with 100 choices, there's 100 by 100 dimensional covariance matrix, it's clear that you need a lot of structure, and this is one way of providing that structure. The concern really is that things may be sensitive to the choice of the nesting structure, and at the same time, this nesting structure has to be chosen a priori. So even though the data are going to tell you sort of how much correlation there is between choices, so back to the single nest, single layer of nest, the data will allow you, sort of will choose the value of rho, will determine how much correlation there is between these choices. But once you specify these nests, you're fixing a priori the correlation between the residual for the bongo burger to be zero relative to the residual for the other two restaurants. And so in that particular example, it's obviously a very natural nesting structure. But in the Goldberg example, it's clear that even if the nesting structure she chose is a very reasonable one, there would be others that would be arguably reasonable as well. And unless you try different ones, it's very, very hard to see how sensitive things are to that. This I think in this 1981 paper by McFadden in this book on Discrete Choice, edited by Mansky and McFadden, he uses this nested Logit model in a much simpler case with just a few, with relatively few choices. And he actually estimates it for all different possibilities of the nest, or at least for a very large number of possibilities of the nest. And you do find that it can make some difference. Now, it's sort of clear that some of the nesting structures are less plausible than others, but it's still somewhat awkward. You have to choose those without, there's always going to be a concern that some other nesting structure may have led to different results. Okay, moving on to the next way of freeing up the independence of irrelevant alternatives. The property is to just directly free up the covariance matrix of the error terms, sort of using normal errors. We could just specify that the factor of epsilon I, the factor of epsilon ij's for each individual has a normal distribution with a relatively unrestricted covariance matrix. Here there's sort of a couple of issues. One is that sort of with more than a couple of choices, direct maximization, sort of direct calculation of the likelihood function is very difficult. It involves high-dimensional normal integrals. Can't do that very accurately for more than 2 dimensions. There's been a huge literature on numerical methods for doing this. So there's the original work by McFadden and Pekes and Pollard looking at simulation methods. These have been much improved and fine-tuned for this type of problem, where we're trying to calculate these high-dimensional multinomial probit models. Those allow you to do this for much higher dimensions. I think sort of certainly up to 10. So I think those things work fairly well. I think the sort of 2 leading ways of doing it now are what is called the Geiwicki-Hasifasiliou-Keen simulator, which sort of partly simulates and partly calculates univariate normal integrals, which in itself is actually very fast. I think it's still easier to do this from a Bayesian perspective, and there's a paper by Geiwicki, Keen, I think, and Rankel in the Review of Economics and Statistics that actually compares Gibbs sampling here and this GHK simulate, and they find that the Gibbs sampling actually works considerably faster. So there you would set it up by treating the latent utilities as unobserved random variables as well. Simulate those in one step and then draw from the posterior distribution of the parameters given the latent utilities in the second step. And both of those things, sort of combining those two steps, the Gibbs sampler is very straightforward, and it's more efficient than these other methods. And so there's a lot of detail for some of these methods in the work by various configurations of these authors of McCulloch, Paulson, and Rossi. It's a book by Rossi and co-authors. And I think this is some of the stuff that Rossi has programmed up. That said, I think so what is the attraction of this method? Compared to the nested logit, it's clearly attractive that now the researcher doesn't have to commit a priori to where the correlations are. You can just, in principle, allow this covariance matrix to be completely unrestricted, other than some normalizations. Obviously, it's a covariance matrix; it's symmetric. Even in the binary case, you would normalize the variance to 1. So there's still going to be some normalizations. But in principle, if there's a reasonable number of choices, there's a large number of elements of this covariance matrix. And there's very little direct information on these correlations. Remember that all we see is what choice individuals actually make. It's sort of very hard to see directly how much correlation there is between epsilon I1 and epsilon I2 if you never get to see the epsilon I1 and epsilon I2 combined. All you're going to see is rankings that epsilon I1 is higher than epsilon I2. So you're going to need a lot of data, a lot of variation in choice characteristics in order to be able to estimate this large number of covariance parameters very well. So in the end, I don't think this is very attractive once you got more than a couple of choices. There's just no way you're going to be able to estimate all of these accurately. And so even though in principle you're safe against you're not making all these restrictions, you're going to end up with predictions about substitution patterns that certainly should incorporate realistic ones, but that don't rule out a lot of values that would have to be that would be fairly unrealistic. And so, in addition to still being computationally feasible with more than 20 or 30 choices, even with choices, I think with 4 or 5 choices, it's very hard to get accurate inferences on all these parameters. And so I'll actually come back to that a little later when we talk about unobserved choice characteristics, because in some sense that sort of explains that these multinomial probit models are without restrictions are far too flexible, allowing for far more general substitution patterns than the data could possibly reveal. Okay, getting now to the third alternative, which is the random effects models. So what this approach does is allow for the slope coefficients in the utility function to be individual specific. And so in some sense that seems very natural in the example I gave before. You can think that individuals who express the preference for Lalims reveal by doing so that they're relatively price insensitive and that they have relatively strong preferences for quality, and that therefore they would be much more likely to go to Chez Panisse rather than the Bongo Burger if Lalims was closed. So how can you capture that? Well, suppose we write the utility for choice j as xij prime beta I, when now the coefficient is indexed by the individual, plus this epsilon ij, which is still the same extreme value or normal error, independent across individuals as well as across choices. Then we can you can sort of rewrite that where you replace beta I by its average, and the difference from its average. So you can write this as xij prime beta bar, where beta bar is the common part of the marginal utility, plus some disturbance. But now, even if the epsilon j's are independent, the new ij's are not going to be uncorrelated across individuals, because there's this component that depends on the choice characteristics and these individual preferences. And so now we're getting this covariance, we're getting this correlation between the unobserved components of the utility. But it's a very structured correlation. It's only choices that are very similar in observed characteristics that are allowed to have they're allowed to be highly correlated. So thinking back about the nested Logit and the unrestricted multinomial probe and this setup here, so in the nested Logit, the researcher had to specify which choices were going to be highly correlated, which were allowed to be correlated, and then the data would tell you how much correlation there actually was. In the multinomial probe, you could free that up completely and allow the data to tell you to be determining all the correlations. Here in the random effects Logit, you're again imposing structure on the correlation structure, but the structure now is coming from the observed characteristics of the choices. You're allowing and so the data would still be consistent with no correlation, but if there is any correlation, it would have to come from observed characteristics being relatively similar. And so the idea would always be that if a particular choice was not available, if an individual has to make a substitution, they would substitute to, they would be more likely than under the conditional Logit to substitute to choices that are very similar in terms of observed characteristics. And in practice, of course, that is what you do in the nested Logit model as well, other than you do it by hand. In that case, you group these choices together in a way that you think they're similar, but typically that would correspond to being similar in terms of observed characteristics already, but you would do so by picking essentially which characteristics you're grouping them on. Now, in terms of implementing this, so that there's different ways you can do this. One way would be to use sort of an approach similar to that used in duration models by Heckman and Singer, to think of there being a finite number of types of individuals. And so in the rest of the example, you could think of some individuals being very price sensitive, and some having very low price sensitivity, some individuals having strong preferences for quality or not. But you could allow for a finite number of types, model the distribution of types, either as being independent of observed characteristics or some function of observed characteristics, and then estimate these models using sort of methods for finite mixtures. These models would be relatively easy to estimate using the EM algorithm or sort of a host of other methods available for finite mixture models. An alternative, and so this is more the way the I/O literature has gone is to model these the types as following a continuous distribution. And so given some observed characteristics, you could model this as the beta i's as having a normal distribution with centered at Ci prime gamma and some covariance matrix. But we may still want to impose some restrictions on the covariance matrix, but where in principle you could allow for a fair amount of generality depending on the amount of data you've got. So the choices between using these continuous mixers versus this finite mixer distribution, again, is one that I think should just largely be driven by convenience. Both are actually fairly straightforward, at least in principle, to do, and both are fairly flexible. So I don't think it's going to make a huge difference in practice. Although I don't have I don't recall seeing any direct comparisons of these two choices, these two approaches. Okay, so having discussed these three alternatives to so these three ways of getting rid of the independence of irrelevant alternatives, let me move on to the Berry, Levinson, and Pecos approach. I remember the days when, at least in econometrics, BLP stood for best linear predictor. Those days seem to have gone. So this has been a very influential approach in I/O. And so what they do is they take these random effects Logit models, but so they do a couple of additional things. One, they allow for unobserved product characteristics. They also, and this is obviously very important in these I/O settings, where one of where the key choice characteristic that varies across choices as well as across markets is price. They want to allow for endogeneity of these choice characteristics, and also they come up with a clever way that implies that they only need aggregate choice data. So instead of having individual choice data, they can estimate their models using only aggregate data. That's certainly extremely helpful. At the same time, there's clearly a huge cost to only having aggregate choice data. In most cases, having individual level choice data is going to make estimation of all these models vastly more precise, especially if there's variation in some of the choice characteristics at the individual level. And so these models work sort of are also particularly well designed for dealing with relatively large numbers of choices, similar to the Goldberg paper. The original BLP paper looks at choices for cars, where there's a large number of choices. So the setup there is, again, where we have a latent utility that depends on choice characteristics that are now indexed both by the choice and by the market. So the idea is that we observe choices in different markets where the characteristics of these choices